Our minds have made an error. We look at these gliding beauties of marvelous complexity, and we think that they and we are something of our own. That life is a kind of indescribable magic. Even Darwin said in his gorgeous conclusion to On the Origin of Species that life was something that had been, quote, originally breathed into a few forms or into one. This completely understandable perspective is nonetheless an error. There was no way for Darwin to know it, but life is chemistry. From diatom to Diana, life is not a magical imbued trait. It is a process of the physics of our universe. The precise and convoluted chemistry of life requires specific physical and chemical situations, and this planet has a dizzying variety of such circumstances that, over millions or even billions of years, living chemical systems have evolved to thrive in. But one thing that is always necessary is energy. A system without energy doesn't just not have life, it doesn't have chemistry. And so the story of life is the story of captured energy. These are oscillatoria, a form of cyanobacteria. Every second of every day, for billions of years, the sun has been exploding, sending energy to the earth in the form of sunlight. And on the other end, or really on our end, are photosynthetic bacteria like these that use the energy of that light to construct chemical complexity. These oscillatoria are gliding toward that light so that they can harvest the energy they need to produce a kind of chemical so powerful, so important, that you will probably be surprised to find out that it's just sugar. Oh, sugar. Such a chemical marvel, just carbon and hydrogen and oxygen, but an evolutionary innovation so fundamental that it remains a primary source of nourishment for even the most advanced living things. You may have seen this beautiful filamentous algae called Spirogyra floating on the surface of water, where it also takes advantage of sunlight to produce its own food. Oscillatoria and Spirogyra are autotrophs. Auto for self, troph for nourishment. In the world of ecology, we call these self-nourishers the primary producers. They are where it all begins. Primary producers can turn the fundamental inorganic components of their surrounding environment into food. In the case of photosynthetic or phototrophic organisms, the energy component of that surrounding environment is light. There are also physical components. They need carbon dioxide and water and nitrogen and phosphorus for building materials. But light is the energy. This is the first way organisms get food. They make it. And most autotrophs use light, but not all. There are also lithotrophs, for example, that use chemical bonds in minerals to thrive. Unfortunately, we don't have any footage of them, so just more Spirogyra for you. And like plants in our macroscopic systems, autotrophic microbes are the starting point of the story of captured energy, because in their bid to hold onto and use that energy, they themselves become balls of stored energy, not just in their energy storage systems like their sugars, but their whole selves are bags of entropically unstable complexity, ready to fall into randomness the moment their chemistry fails. I think we have to understand here that randomness is the natural state of the universe, not because of some inherent evil But just because there are literal trillions of random ways for atoms and molecules to be scattered about, and a vanishingly small number of ways in which they will be organized. And so, fighting randomness, that is the cause of life, and that fight both requires energy, but also definitionally stores energy. Because an organized state tends toward disorganization, the path down that hill is one that releases energy. And as that energy is released, it can be captured. And if it can be captured by another organism, it can be exploited. And so we have our second system living organisms use to stay alive. They don't make their food. They eat it. Single-celled eukaryotes, also called protozoans, dine on autotrophs, digesting their organic components to supplement their own bodies with the nutrients and energy they need to grow and survive. And from there, nature weaves the complexity of the food web, transferring nutrients and energy through this network of organisms consuming other organisms. Protozoans eat protozoans, and sometimes even a few metazoans, the microscopic multicellular organisms like rotifers, water bears, or fat flatworms. And then you get to metazoans that eat protozoans like Daphnia, which in turn gets eaten by a fish, the microscopic now transitioning into the macro. These eaters consolidate the energy, not just keeping themselves alive, but feeding the more complex chemistry, pushing themselves further and further from randomness, further and further from the equilibrium state. But in the end, no matter what, life, neither big nor small, lasts. Eventually, through random chance or wear and tear, the chemical systems maintaining this far from equilibrium state break, and the living chemistry ends. And so we have our final opportunity for energy transfer, the last link in the stored energy chain, the decomposers. As microbes and plants and animals alike die, they decompose into the environment, their bodies broken down and recycled by organisms like this paranema, which is usually found among decaying organic matter. Here you can see its mouth, called the rod organ, through which it takes in bits of decomposing matter and sometimes just other organisms, and eats them, converting them into carbohydrates that it stores in those shiny paramylon grains. Though these decomposers come at the end of the food chain, well after the sunlight that started it all, they are still surviving on that stored energy originally flung out from two atoms fusing in the core of the sun. And of course, the role they play in our ecosystems is still vital as they break down once living organisms into their chemical building blocks. They release those nutrients back into the environment, ensuring that those building blocks are available to the autotrophs that will begin the cycle all over again. As we delve into more and more ecosystems, the vast number of factors that have shaped a microbe's evolution become more and more apparent, but one thing remains consistent: the chain of stored energy, the primary producers, the eaters, and the decomposers, sustaining the chemical system that keeps them complex, the energy that holds them together, and that is holding you together right now, preventing you from simply falling into randomness. This is a ciliate, Loxodtes magnus. It is about to die. Of course, depending on your time scale, we're all about to die. To the Grand Canyon or the sun, things that have existed for millions or billions of years, we are each weird little bubbles of peculiar chemistry that form and then pop, form and then pop. But this ciliate, and with our new microscope you can really see those cilia beating, is about to pop right before your eyes. It looks fine right now. You can even see inside it its last meal, a Trachelamonas, so we don't think it's starving to death. It seems to be trucking along just fine. Loxodtes magnus are microaerophilic organisms, preferring a low concentration of dissolved oxygen in their environment, but not too low. So maybe the concentration on the slide was too high, though we've witnessed many others who have been just fine in our preparations. So no, we can't tell you why this ciliate is about to die, but we can tell you that right here, that's where James, our master of microscopes, first saw something strange. The moment the ciliate shifted direction, a little trail of cell membrane and cytoplasm. No reason, nothing grabbed it. It didn't snag on anything, but a little bit of what was once part of the organism was suddenly no longer a part of it. That cytoplasm is full of complicated molecules that are what chemists would call far from equilibrium. Equilibrium is the situation in which chemicals no longer have a tendency to react over time. In general, a thing that you can say for sure is that all the stuff outside of living cells is either at chemical equilibrium or it is headed there, whereas stuff inside cells is not at equilibrium, and it's not headed there either. How are all these chemicals that, if left alone, would rapidly reach equilibrium, managing to not do that? Life. That is what life is. A bunch of chemicals that take in energy in order to keep each other from reaching equilibrium. Quick break from our friend. The way we define life in biology classes is wrong. It's not even really a definition. It's a set of qualifying factors. Life has to take in energy. Life has to reproduce. It must respond to its environment. It must consist of cells. This is not a definition. It's an attempt to draw a line, to create a boundary. And that makes sense for things that are actually amorphous and complicated, like social constructs. But life is not a construct of our opinions, but of reality. Life is a chemical system that uses energy to keep itself from reaching chemical equilibrium. Why did they do it? Oh, well, maybe let's not go that deep, at least not today. Suffice it to say, a system that did this developed on this planet, and now, billions of years later, it is still doing it. We have many things in common with this ciliate, and not to belabor the point, but one of those things is that we will die. You've probably noticed by now that this video isn't about what life is, it's about what death is. It's just that first, we had to define life. Life is chemicals working together to take in energy to keep themselves far from equilibrium. Death is not the return to chemical equilibrium. The process of decay can last decades. Likewise, many parts of my body will return to equilibrium over the course of my life. I'm shedding skin cells right now, and so are you. The atoms and molecules of my body are replaced with new ones over and over and over again, but I will only die once. Likewise, our ciliate has been shedding cytoplasm and cell membrane for minutes now, and that shed cytoplasm is dead, no doubt, but the organism lives. Its chemistry continues, for now. Death is the moment when the system that maintains the far from equilibrium state ceases existence. And we can imagine that at many scales. That can happen to individual bits of an organism, as it is happening to the chemicals spilling out of our Luxotes right now. It can also happen to an individual cell in an organism, and that happens all the time. It is happening right now inside you. It can also happen to an organism. That's what we usually think of as death, with our focus so often on the individual, but we can keep moving up the scale and find yet other kinds of death. When a common genetic system that was useful for keeping many similar but individual organisms alive ceases to exist, that is an extinction, a kind of death. And when the system that has kept all life on Earth far from equilibrium for billions of years, that system that we all share of nucleic and amino acids, when that ceases to exist, that will be something else. A terrible kind of death that we do not even have a name for. But it will be a death. The largest death, I suppose, until heat death, when everything in the universe has found equilibrium. Our ciliate is about out of time now. I don't know when we can call it, when we can pronounce the time of death, but this seems as good a time as any. Here, we have death. The system that was using energy to keep itself from reaching equilibrium has ceased to exist.